So you have to turn in the homework for the next week, on the week after next, on April 22nd, and you have to turn in the homework for the microfluidics, essentially the one that's coming up next week, on the usual time on April 24th. I will be at the Materials Research Conference in San Francisco on April 22nd, but because we have a discussion, you're going to carry on without me. And I'm going to watch the discussion all on the internet, so kind of, consider me present. But as a leader for the discussion and some person whom you may want to meet, I have invited Marty Hubie, Professor Marty Hubie, from the paper science department, who is a specialist in colloid science. So he's going to lead the discussion, and he's specialist actually on nanoparticles. Now, then we're going to have the lecture on self-assembly and photonic and electronic materials, which is really my specialty area. Then the discussion on April 29th is going to be postponed. I'm not going to be here. But in the last lecture, we have a review, which we're going to combine a little bit extended lecture with a discussion on nanoscale engineering, which is going to be actually a pretty good review of everything that we have studied, together with the review and the discussion. And finally, you have the short-term papers, which typically would be your discussion topics, which you have presented, expanded to a short-term paper, unless you would like to change it, for which you let me and Angelica know. The short-term papers will be due 1 week after the end of the course, that is on May 5th or May 8th. So this is what we have to do yet in order to finish this course and wrap up all the knowledge that I would like to kind of pass on to you. Any questions?
So basically we have 2 more homeworks besides
right.
one that's due this week.
Right. You're going to have one homework for this week, which is going to be posted on Thursday and which is due on April 22nd. You're going to have one more homework, which is going to be quantitative, which is going to be posted next week and which is going to be due on April 24th. You're not going to have a homework for this week or for that week, so essentially the homework which is going to be posted next week is your last homework. But this is going to give you the opportunity to start working on your short-term papers, which are due 1 week after the end of the course. Okay, and we would like to study microfabrication today, but before we go to microfabrication, I still have a few important slides on the dynamic light scattering, which I think you should know as people who are going to do some practice in that area. Whatever you do in colloids research, sooner or later you end up doing light scattering just to characterize your system. So let me just give you the basics again very briefly before we move on. If you remember, this is what the light scattering equipment looks like, and we have one in our department run by Professor John Van Zanden's group. You have the laser, you have the cuvette, which is thermostated. You have the optics focused on a specific place right in the middle of the cuvette, and you have the photomultiplier, which very fast records and sends the data to the computer. Now the computer also have kind of the most special piece of equipment, maybe not these days, is the so-called correlator, which allows very fast calculations inside the computer of time-dependent light scattering processes. We discussed static light scattering. Obviously static light scattering is easy. You just record the intensity as a function of the angle, for example. Now what is the problem with static light scattering though? And it is not that big a big problem with dynamic light scattering. If you remember, if you have proteins, for example, what's the problem with light scattering? A practical experimental problem that you have to solve.
The wavelength is much larger than the size of the particle.
Right, but you can do light scattering. You can get the form factor. You can get information about the shape of the protein, but in principle you can still do scattering. I mean, you can get the structure factor. You can get the second virial coefficient. What is the experimental problem with static light scattering though?
Dust particles.
Right. I mean, if a dust particle locks in your beam, you're going to have scattering which is so strong that all scattering from protein is not going to matter. So you are going to get something that's totally off the scale. So you have to purify your samples very carefully. This is not that a big problem for dynamic light scattering, because what you do in dynamic light scattering is you are measuring the intensity of the light which is reflected from a particle. And you're doing this in a very fast time scale. Let's say this is some nanosecond time scale. Now, why do you have these fluctuations in the intensity, even if it's a single particle? I mean, it's actually written here, although this one wouldn't write. Brownian motion. So every particle is subject to the thermal motion, and it is going to jump around. Now, obviously, if it's a smaller particle, it's going to jump and stop faster or slower? Faster. I mean, going down to the molecule, which really moves very fast and hits other molecules all the time. So obviously, if you measure the intensity, you are going to have now this intensity changes because the particles moves towards the detector or outside the detector. You have scattering from other particle which interferes with this scattering. The point is that the reflected light is a function of the movement of the particle. And you can see that actually it's a function of how fast the particle moves reflects how fast the light is going to fluctuate. So if you have a mathematical means of correlating these fluctuations to the particle size, I mean, you are very happy, right? I mean, that's what all this exercise is about. And the parameter that people use for in this case is the so-called correlation function. I'm going to define mathematically just on the next slide. It just tells you that if you have a larger particle, these fluctuations are going to take longer time. So the fluctuation is going to decay slower than in the case of small particle. If you have very fast means of kind of measuring the fluctuations, you have also the means of finding the correlation function. Now, usually it is defined as autocorrelation function. Now, these brackets means what? Time averaged. So you have to take results, numerical results for some time and average them. So it's the time average of the intensity at a certain moment times the intensity at a certain moment plus a certain kind of interval of time. So actually this is a function of the interval of time here. The longer this interval, the more uncorrelated the two fluctuations are going to be. Kind of it tells you in a sense mathematically, it tells you how far in time a certain process extends, whether it's a short process or a long process. So when you extend this period of time, any process is going to go to zero. I mean, it finishes after some time. And then this function can be also correlated to the diffusion coefficient of the particle, that is, how fast the particle moves around. So then, if you measure this function, and then from this function you can immediately measure the diffusion coefficient of the particle. Then, of course, you can plot the data in a way so you can fit the diffusion coefficient, and from the diffusion coefficient, if you're chemical engineers, you certainly know this formula, Stokes-Einstein equation for the diffusion of a sphere, thermal motion divided by hydrodynamic resistance. The parameter here that you're looking for is the radius of the particle. So you have the opportunity to kind of determine the radius of the particle from this function, which the computer actually calculates by using a very fast module, which actually does the measuring of the light intensity and calculations. The bottom line is that you get the particle size. With more luck, you can fit kind of like the results to a certain, let's say, certain set of autocorrelation function, and you can obtain a certain set of intensities which will be eventually fitting for polydispersed particles. So that's how this equipment works. Now there are some buts here and some not that happy things. Now I have these bumps here. So the one bump, like kind of not a very big problem, is that the scattering volume has to be small. So it has to be well focused, and you have to work at the smallest aperture possible, which is usually fulfilled by the people who make the instrument. You have to make sure that your instrument is aligned properly. Now, if it's aligned properly, now fitting assumes that spherical particles is unreliable for complex size distributions. So in a sense that if you have very polydispersed particles which are not spherical, the fitting is going to fit something, but it's going to fit function which is not close to reality. Just because this model assumes kind of like, civilized, mild distribution function. So anytime you get data which looks very polydispersed and which has some peaks here and there, you have to be very suspicious whether your fitting procedure was right or not. And finally, the most common problem, this is really very common and very unpleasant. Now the samples have to be diluted, because this mathematical model assumes that you don't have multiple scattering. You have the intensity that you measure is intensity from single particles. It does not go through other particles which distort the data. Now diluted means, from the practical viewpoints, it means samples which are almost transparent. Essentially transparent, you just have see a very, very small kind of, let's say, translucency. What is a very common error is kind of, like a graduate student or an undergraduate, whoever has to do some research. He goes to the light scattering equipment, kind of like reads the manual, pours some milky sample inside, and gets some data which is total junk. If the sample is not really transparent, you're not getting really reliable data. Now, luckily these days people have done what is called fiber optics, DOS, which allows to dip the optics in the sample and allow and receive data even without diluting the sample. The reason you can do that is because the fiber optics measures the autocorrelation function directly on top of the fiber. In the usual equipment, it has to go through suspension and come back. So that's why it has to be diluted. But again, you have to be very careful what types of data you obtain. Now, this is one of the methods which can give you very useful data, but it can also give you very junky data, and you are never going to find out unless you take care. Because the computer always fits the results and gives you printout. It doesn't know whether you diluted the sample or not. So that's about light scattering. Any questions so far? This is a wrap-up of the previous, we had to finish this from the previous lecture. And the rest of this lecture will be fun. Like no formulas, just looking at different fabrication methods.
So knowing the correct dilution is just sort of trial and error in practice? So
Yeah.
Get the expected?
Right. You also have to have sufficiently enough counts. So if you dilute your sample too much, you're not getting any counts. But the problem is that if you can get many counts, but it can be overly. So you dilute it until you see the counts going down, and that is about the right dilution. So if you put in a sample and start measuring the counts, let's say this is counts, this is concentration. Okay, and so then the counts are going to go something like that, and then they're going to level off. This is the milky kind of case. So you would like to be somewhere here. Some equipment these days can have some programming kind of warnings and so on, but usually it doesn't, and that's why people obtain lots of crap eventually, just by not knowing these requirements. And again, when you think about colloids, you don't think that it should be almost transparent, but that's how light scattering works, dynamic light scattering works. Static light scattering doesn't care. As long as the light goes through, you're fine. Or almost. But dynamic light scattering needs diluted suspensions, or otherwise you get junk autocorrelation function and junk results. Okay, so let's have some fun then. Now we're going to speak about microfluidics, chips, bioRS next time and so on. But then as kind of future colloidal engineers, let's say, nanoscale engineers, you would like to kind of know, just have a general overview of the area of micro and nano fabrication. So how do you make these devices, and what options do you have, what is expensive, what is the limitations. So this is what this lecture is about. That's what I'd like to tell you a little bit here. I'm going to focus mostly on non-lithographic methods, but if we have to go to non-lithographic methods, we also have to define what lithography is. Now these are examples of things that you can do these days by microfabrication. All those small machines which are very cute but don't work that well, if you remember, MEMS, which are comparable in size of, this is a mite. You can have, if you remember, we discussed this in the lecture of contact angle, where you can have micrometer scale droplets with specific shape on a surface. And in this lecture we're going to study how you can make a surface like that, which has a pattern, which has different wettability. You can have, this is something that you are not likely to do, at least not in chemical engineering, order a coral of atoms, magnetic atoms for example, which have some specific quantum property. And this coral is made by what? This is a very widely shown image. Right, yeah, exactly. I will mention that. Or you can make three-dimensional structures with periodicity, or supposedly photonic structures, albeit on a macroscopic level, by using, for example, photolithography and photopolymers. Who mentioned that briefly. Now, this set, the most common way of doing lithography these days is photolithography. And the reason is what? Because it's used in semiconductor technologies. Some of you may know a little bit about that. I would like to go briefly through the method so you have just the basics of how it works. You have let's say a silicon wafer. A very nice, clean, flat silicon plate. Now, usually you would like to make structures in glass rather than silicon. And how do you make glass out of silicon? You oxidize it. So you oxidize the surface, you have this oxide layer, which is glass, essentially, silicon oxide. Now then, in order to be able to embed the features, you cover this with a photoresist layer. A polymer which can polymerize under illumination. Next, of course, you need to embed the features that you want. So you take a glass plate, which usually typically has a metallic patch, intransparent. You put this on the surface of your photopolymer, and you want it to be as close as possible. And then you illuminate by UV light. What happens is that the photopolymer, which is illuminated, gets polymerized. The photopolymer, which is not illuminated, remains in kind of monomeric or oligomeric type, so it can be dissolved. So this one, for all purposes, is already a solid polymer. Then you take off the mask. You have two types of polymer here. This one dissolves easily. You can dissolve it. And you have this photopolymer layer on top of your glass layer. You can then etch your glass layer by using hydrofluoric acid, nasty stuff. And then if you are a guy who is about to make a microprocessor or something in semiconductor, you would like to actually proceed and embed something in the silicon. So then you can remove the photopolymer. You can use this glass layer as a mask for embedding something like some type of semiconductor feature. And then you can remove the glass layer, and you end up with this semiconductor feature or transistor or whatever in the silicon. For our purposes, however, what we are interested in, we are more interested in this feature here, which is the three-dimensional channel that you can make by using photopolymerization. Why you are interested in that? Because this is the basics of microfluidics, which we're going to study next time. This is how you can make different types of thin channels. And I have actually copied here. Sorry that you can't read this on screen, but you can read it in your printouts. I have copied here what is the typical industrial process for fabrication of microscopic channels these days. You take a glass plate, put in a layer of metal, put in a photoresist layer on top. You have the mask which transmits light. This is actually another type of photopolymer which gets dissolved when it's illuminated. Transmit light, so you dissolve the photopolymer, you can dissolve the metal below. Then you can use this protective layer to etch a channel by using hydrofluoric acid, for example, inside the glass plate. Once you have done that, you can take another glass plate, put it on top of the first one, put some glue or just heat it up, and you're going to have this all glass channel embedded inside the glass plate. This is the technology, not that simple, not that cheap, but well reproducible method for making microfluidic devices and microfluidic channels. So that's how it works. It's a simple process, but as you know, it's not that easy to make experimentally, and you can make some laboratory modification as some of the people here are trying. So it has a variety of options. Now, before I go further, any questions about the photolithography in general, how it works and so on? There are some things that you need to take care when you do that. The photopolymer layer has to be of appropriate thickness. The mask needs to be closely to the photopolymer surface. You need to get rid of dust, of course. And actually, kind of the technology is amazing because in order to make a, let's say, a semiconductor chip, a microprocessor, you have to repeat this process tens of times, making millions and virtually billions of features on the surface. So the fact that present-day technology has allowed to make microprocessors and so on is really amazing in terms of how well it works. Now, from the viewpoint of chemical engineers, this is not that good news. And the reason is that kind of as chemical engineers, we always try to come with some clever methods for patterning, structuring, microfabrication, and so on. And it's very easy to demonstrate some rudimentary principle for microfabrication. But replacing a technology which is used in thousands of places around the globe and which works so good and which has billions invested is not that easy. So many of the microfabrication efforts that you hear around are very nice, but you can doubt whether they're going to make any practical sense in the near future. Although some aren't. I'm going to discuss some methods like that. Now, Daniel here had a question.
No, I was just wondering with the metal channel if you can still induce electroosmotic flow.
You may want to leave the metal for electroosmosis and so on. Now, in this case, the metal is used as part of the mask. Well, what kind of like for technological purpose, people would like to use the metal when they etch the glass. This can be used, for example, in many cases you can do, for example, vacuum chemical etching, which the metal can be a good mask. So in this case, the metal is sacrificial, which means one that is used only for the purposes of fabrication and then removed. Sacrificial layer, which is just made in order to etch the channel.
Do you have a problem with the limitation in the narrowness of, say, that's a thin slit?
Yeah, I'm going to show the limitations of different methods, but the best kind of and this is a very big problem now. Right, I mean it's related to diffraction now. The diffraction is related to what? The wavelength of light. And the smaller the wavelength, if you remember, actually we discussed this formula when we have been discussing when we have been discussing microscopy. The resolution limit, I think we use R there. The resolution limit is equal to the numerical aperture divided by some constant times the wavelength. Let me see, the wavelength should be, actually times the frequency. It should be frequency here. The higher the frequency, the lower the resolution limit. Okay, so this should be omega. Or you can put the wavelength on top. So the higher the frequency, the lower the resolution limit. And the higher the numerical aperture of the optical equipment, again, the lower the resolution limit. Now these days people, so obviously in order to decrease the features, you need to use shorter and shorter wavelengths. And that's why these days people think about what's called extreme UV lithography. And you have heard probably about the facility that Joe De Simone has kind of secured for as an extension of the CO2 center, which is essentially one facility which allows microfabrication of the extreme UV light. These days such devices go to about 300 nanometer type features in size. Now can you do something at smaller features?
Another doing research on 190 nanometers.
Yeah, I mean it's about 300, 200. I mean, industrially, the industrial chips these days are about 300 nanometer features. Like the research these days can go to 200. They have this 190, but now 190 is actually more the wavelength rather than the feature.
Yeah.
But this is the size of, it's still above 100 nanometers. Now, can you do something at higher resolution than that? No, you can actually. I mean, like, you don't look that enthusiastic, but you can, and it's very easy, and you can do this on campus right now if you have enough money. And it's actually fairly simple. It's not as simple as a technique. It's simple to use because you are actually not you just have to make a design. Now, until the question is like that, now it's the hen and the egg question. Now, if you have photolithography, you need a mask. If you have a mask, you can do photolithography and you can make more masks. How do you make the first mask? Because you see that this essentially reproduces the mask. Well, how do you print on the nanoscale?
Electron.
Yeah, I mean, it's called E-beam. E-beam is essentially, and that's my next slide actually, E-beam is essentially, E-beam lithography is essentially the inverse of scanning electron microscopy. If you remember, in scanning electron microscopy, you have a beam which scans the surface and which tells you the features on the surface, whether they are conductive or not. Right? Now, imagine that you have a kind of like gullible surface and you have a very strong E-beam. You are essentially bombarding it with a flux of energy. So if your beam is strong enough, you can, instead of visualizing the surface, you can use the beam actually to kind of evaporate and touch the surface. And because you have the scanning system already there, I mean, you can just program the equipment, how it's going to scan and when it's going to kind of increase the intensity so it burns through the surface. You can put in a thin metal layer, what usually people do, and then you can use the beam to essentially burn out and evaporate some of the metal, so you're left with the features that you want. The problems are, of course, that this is a very complex equipment, very expensive. You have to work in vacuum. And the problem is that it's made in a way by writing, right? So it takes time and it takes money. So that's why people use it to generate the first mask. And then after it's generated, you can already make cheap copies. We have had some research which still has to come here with Ketan, who is smiling shyly over there, being reminded about that. But we had a mask of 1 micrometer features generated, and it costs $1,000 per mask. So, I mean, it's expensive. Now, all those processes are also made in ultra clean facilities. You have heard about different types of clean rooms, class 1, 2, 3, 4, and so on. You have seen those people working with like almost like astronauts. The point is, why do you generate a mask which has a 100 nanometer features if then you drop a single one like 10 micrometer particle on top of it, and then your microprocessor is gone. I mean, right? it's like putting an enormous piece of junk right in the middle of your design. So that's why it's very expensive. This is an example of what type of features you can get. You can see that this is 200 nanometer. This is 3 to 5 nanometer wide lines. So this is really nano, really nano science. Or you can have these nanometer features which are about, this is 40 nanometer, this is 200, so it's less than 10 nanometer per dot. So you can make this really nanometer scale features by using e-beam. It's not that easy and it's expensive, but it is kind of the one that generates the first egg, which is the mask, and then you can make hands from it and so on. But I mean, you need something to generate your mask initially. So a typical photolithography process, you design your mask, go to the e-beam facility, pay them, get your mask, and then start doing photolithography.
What's the material of the mask?
Usually people prefer to use the most typical is chromium, thin chromium layer on top of quartz. That's the industrial standard.
Get the lecture on the TV.
Chico, can you turn on the lecture on the TV on top? Okay, here's me. Okay. Let's move on then. Now this was kind of, you can consider this hard lithography. But as a colloidal scientist, I mean, like we don't like vacuum and we are not really working with e-beams and so on. So we want to kind of, can you do lithography like in the lab at very normal conditions and so on. And I mean, this is really one of the biggest kind of contributions to science of scientists whom we have discussed here, Whitesides. He came up with this idea, which is, I mean, you can see that it's as simple as printing, just the way you do stamping actually, nanometer size features. Now, in order to do that, we need some ink. And the ink in this case is self-assembled monolayers. You remember from the lecture that if you use alkane tiles on gold surface, you have something that we can call absorption from the viewpoint of colloids, but it's actually so strong that it's almost the equivalent of chemical bond. So if you put alkane tiles or gold, they stick hardened essentially very strongly and they don't move around too much. So then you can think of this as being kind of a molecular scale ink. You can deposit a single layer of molecules, and this layer of molecules is going to stick there. And if you can pattern this layer of molecules, then you have kind of in a way surface patterns. Molecular ink by using molecular ink. Now the question is, how do you put those molecules on top of the surface? And you can think of some incredibly complex methods of like moving molecules or something like that. But Whitesides has come with the idea that you can just stamp them on the surface, just like you do rubber stamping. And this process has been called subsequently soft lithography. It is being explored these days for technological purposes. We'll discuss this a bit later. Now, first, how do you make the stamp? Of course, by using photolithography. So you generate, let's say, some features on a photo by using photolithography. Then on top of this feature, you pour what the water stamp's made of rubber. You put silicone rubber. You cure on top of it, polymerize a rubber which is called polydimethylsiloxane, essentially silicone rubber, which reproduces the features here. Then you peel this off, and you have this rubber stamp, with those thin microscopic features protruding from the surface. How do you do the lithography itself afterwards? You can take this stamp, put it in contact with alkane tiles. They're going to adsorb on the surface. Surfactant absorbs on rubber. Then you just stamp it on the gold, and in the regions where it's going to touch the gold surface, you are going to have the alkane tiles immediately sticking, attaching to the gold. You just peel off the rubber, and you are left here with layers of alkane tile. Alkane tile is a kind of, it's a hydrocarbon, so eventually you can use it as a mask to etch the gold. The gold is going to be protected here. You can think of this as a very thin protective layer. It can protect the gold, or it can be used to deposit something on top. And it's going to use very much like the mask that we have shown. Now, you can think like if you want to, of course you say, well, I want to kind of like make this process fast and practical. So you can, because it's silicone rubber, I mean, you can just put it on top of a roller, and you can potentially roller stamp on top of surfaces very much similar to the way you do printing, for example, of newspapers. Or you can do more complex techniques where you have this glass cylinder rotating, transferring, let's say, transferring the features from this one to that one. But all of it boils down to kind of essentially rubber stamping of thin organic layer on top of the metal. And this is an example of some of the features that have been made that can be made by such a method. This actually is from a paper of Whitesides and one of his most notable students, Yunan Jha, who visited me and presented a departmental seminar last year here in our department. We're good friends with him. You can see you can very much make different types of features which very much resemble the features you made by semiconductor technologies. And you can think, now we know about wetting. We know that if you put hydrocarbon, it does not wet well by water. So just when you kind of rubber stamp these features, you can also use them for different types of wetting, nucleation, and so on. So essentially this pattern which I showed to you is made by rubber stamping of a hydrocarbon layer here. So you have a clean surface which is wetted and the surface which is non-wet. So if you dip this in water and take it out, the water droplets are going to spread in this kind of featured droplets on the surface. If you put some chemical inside these droplets and then dry them, then this chemical is going to dry and then form a small crystal on each place where the droplets have been. So then you're going to have an array of, let's say, small crystals deposited inside these chambers. And you can use this chemically to deposit different metals and so on, make three-dimensional features from metals. Now, this process has been very much discussed in terms of technology, but somehow, simple and nice and good as it looks, it is not technologically, by no means it does not beat technologically these days the photolithography. It has a variety of problems. Ink leaking, rubber stamps may get a little bit kind of disfigured, deformed, and so on. So technologically, still nothing beats photolithography if you have to make semiconductor chips. But for a variety of other applications, soft lithography can be quite good. Let me show you this comparison. I'm not going to go through all of this here. Now, this is made by the people who do photolithography. So in a way, it's a little bit of advertisement. Kind of, I mean, it's the best possible case for soft lithography and not that good case for photolithography. But it kind of defines now what do you use: rigid photomask, elastomeric stamp. What can you do? You can do photoresist and so on. You can argue that you can make a variety of chemical features by using soft lithography. It can be argued that this is a planar technology, while this one can be also three-dimensional. I don't buy this argument that much. So you can, in this case, you make two-dimensional structures. In this case, you make two-dimensional and three-dimensional. And then it can be argued that this one has a higher resolution. But this resolution comes at some price here. So while the photolithography presently has about 250 in reality and 100 in laboratory features, soft lithography in laboratory condition can go down to as small as 30 nanometers with some strings attached to that. So the minimum feature size is essentially comparable. These people claim that soft lithography can be smaller in feature size, but again, that can be arguable. So this concludes the soft lithography part of the lecture. Now, any questions here? Any kind of like, Daniel seems to be kind of.
I don't have a question.
It's a very beautiful method, and it's not that difficult to implement in your lab. Yes, Selene?
The stamp for the soft lithography, that's
Uh-huh.
made using the photolithography, right?
Right. Well, yeah, you have to, I mean, like essentially, the first stamp will be made by using E-beam.
Yeah.
So you make a mask by E-beam. Then you take this mask and you put this mask and you do photolithography. Then once you do photolithography, you kind of generate the features by etching. And then after you have etched, you have these three-dimensional features. Then you reproduce into the soft lithography stamp. Now this kind of tells you that, I mean, like it's arguable that photolithography can be claimed to be only two-dimensional method, while soft lithography can be claimed to be also three-dimensional method. Because if you have to make a three-dimensional structure in order to make the stamp, right? But soft lithography has a variety of interesting features. Now, one area of research, which is not kind of like, I mean, shown here, is, let's say you have your mask, then you put your mask on the top of a surface. So you're going to have these channels which are closed by this rubber stamp. Now then if you fill up the channels with something, which can be colloidal particles if you like, when you peel off the rubber stamp, you're going to have like structure of particles on the surface. One very simple way to do particle structures in 3 dimensions on a surface.
Why is that soft lithography?
Huh?
Why is it that just?
It's called.
I mean, are you putting down a monolayer in that case?
No, what you do is like you put your you put your rubber stamp on top of the surface, and you fill the channels between the stamp and the surface by just you pour liquid through them to it particles, and the particles get deposited in the channel.
But that doesn't seem like it has to be unique as a rubber stamp. It seems like you should do it with photopolarization.
Yeah, you can. Yeah, right. But yeah, photopolymerization will be. I mean, like when you do photopolymerization, the problem is that at the end, you have to dissolve the photopolymer, right?
So you're left with the channel.
Right. So you can make a photopolymer channel, then fill it up with something, and then dissolve the photopolymer, right? Hoping that the something that you have deposited is not going to come off when you dissolve the photopolymer.
You can't dissolve the photopolymer.
Not the one that you're working with, but there are other which is soluble. Your photopolymer is specially made for microfabrication. So it's polymer which is not supposed to be dissolved.
The thing I think that's important about soft lithography is that you don't have that solvent etch step. So you eliminated the organic solvent piece.
Yeah.
which is big.
And at the end of the soft lithography, you just kind of, I mean, like the end of the soft lithography is exactly like that. Just peel off like some rubber from the surface. So you don't have to dissolve it, and you don't have to subject it to harsh conditions and so on. Now the problem with soft lithography is in a way it's kind of a softness, which makes it so easy and nice to work. It is also a problem though. Now imagine that you want to make a semiconductor chip, which these days is, let's say, it's relatively large. Now imagine that this is the semiconductor chip enlarged 10 times. Now if you do photolithography, you have a quartz mask, which you reproduce in the semiconductor. Now if you have soft lithography, this is a silicon rubber mask. Now, but this silicon rubber does exactly what this rubber do, right? Deform, stretch, and so on. So it's very difficult to make sure that next time you put the rubber down, you're going to have the features exactly where you want them. So the fact that it's soft actually is the one problem for fabrication. You can put it easily, but how do you know that the features here are not going to be a little bit displaced just because it's rubber and it can deform? Wow, a mask which is quartz is never going to get significantly deformed, if at all. So that's the problem for semiconductor. But people are thinking for a variety of other applications. If you want to feature something without caring exactly, just make some patterned surface, like these days for magnetic hard drives, you can just stamp it. The other problem with soft lithography is, as you can see here, okay, it's not exactly shown, but here you're stamping with, this is the active, the surface which you're stamping with. But you also have tile here. If you keep repeating the process, the tile is going to eventually fill up this channel, and what's going to happen is very much what happens sometimes with rubber stamp. It leaks. So you have to stop and clean the stamp, and that's not something that you want to do in technology very often. So that's it, but in terms of applications, it's great. This is something that you can do in your lab and stamp. Okay, now what is one other type of, this is a cute image, one other type of instrument which you can have in your lab. It's not very expensive these days, and which allows you to make features. You have certainly all heard about atomic force microscopy. Just for the people of you who haven't worked with that, essentially what you do is you are scanning the surface with a sharp tip, and you are measuring the deflection between the tip and the surface. What you can see here is the tip moving, but in reality, in most of the FMs, the thing that moves is the surface actually. So the surface is attached to this piezoelectric tube, which has electrode which allows it to tilt in this direction or in the direction perpendicular to the board. So when you apply voltage, this tube tilts, so the tip essentially scans the surface. And when it scans the surface, it's going to deform, obviously, because you have different features. So when it hits a feature, it's going to deform. Now you have this optical system, a laser beam focus on the end of the tip. So when it deforms, the laser beam is going to get deflected a little bit. If you have the laser beam falling on a photodetector, you can detect this deflection of the laser beam corresponding to the deflection of the tip electronically. And then you have an amplifier and computer which relates the position to the tip, to the deflection, and then you generate a three-dimensional image. Also, it's a two-dimensional image of the deflection of the tip. You can make it a three-dimensional if you like by just plotting the deflection in one direction. This is almost a real-time scan of how it works. You can see this is the tip here. This is what it looks like. You can see the laser beam kind of being deflected from the surface here. It is made to look as if it scans the surface, but the reality is that the surface gets scanned. And the reasons why you prefer to move the surface than the tip is what?
Calibration.
You don't have to align the beam every time.
Yeah, right. It's kind of, you can tell calibration, but more precisely, if it moves, how are you going to follow it with the laser beam? So you want the tip to be immobile, and the laser beam will be deflected, and the surface to move. Okay. So now this is how it works, right? The question is how can we use it to do different types of fabrication, and because this tip drags along the surface, you can immediately say, well, I mean, maybe we can visualize things, but maybe we can also move things around the surface by using the tip. This is an example of the highest resolution that you can achieve. You can really see down to atomic scale. This is actually these are the crystal. This is the crystal surface of some specific material. So you can see atoms here. Or if you have atoms on the surface, now this is an image which you're going to see in any popular description of nanotechnology. And it's an image which is already 14 years old. The people who discovered the AFM then used it to move argon atoms. I think this is argon or neon atoms on the surface. So you can take an atom and move it on the metal surface, and then it's going to stay there. Then you can use the same tip to scan along and visualize what you have done. So this was kind of like one of the very strong motivations, that you can move things atom by atom, and you can do whatever you like on the smallest scale possible. This was, of course, one of the most successful Nobel Prizes, even though the original paper didn't get accepted in Nature or Science. I mean, kind of somebody said, what is this kind of crap, some scanning technique and so on. I mean, like, so they originally rejected the paper. But finally it led to a Nobel Prize. This is an example of what people do these days. You can organize these metallic atoms, and you have this coral, and you can actually do quantum studies on the waves in this coral. So this is essentially the electrons in between the metallic atoms. The electrons essentially resonate between the atoms like a chamber. So this is visualization of the quantum kind of level of the electrons inside the material. And again, this is made by ordering the atoms by using KFM. This is made by a company, the company which has pioneered this area is ABM, of course. So there is still quite a bit of research that's ongoing. Now, none of us is likely to chase atoms and study quantum effects. Somebody may, but I mean, most of us won't. But then what can we do in terms of colloidal science? This is the so-called deep end lithography by a scientist, Chad Merkin at Northwestern University. Actually, most of this stuff has been developed previously by others. We'll have self-assembled monolayers, right? So we can take the FM tip and use the FM tip as a kind of a paintbrush for self-assembled monolayers. So we can dip the tip in like a droplet to its surfactant, and then we can move the surfactant around. After this, dry the tip and then move around the surface and visualize what we have done. So first we use this as a paintbrush to paint surfactants on the surface, and then you use the tip after you wipe out the paintbrush. You use it to visualize the surface. So this is, for example, these are different modes of AFM, just different types of visualization. This is a shorter time, longer time, even longer time. And the reason it spreads out is because the surfactants diffuse. So you put it here for a shorter time, some surfactant spot. You put it here for a longer time, it diffuses around and so on. So this is the equivalent of, like in all those paintbrush programs, you have the size of the brush, right? And then you can make different features like arrays. You can draw different features on the surface. You can see that this is from here to here is 4 micrometers. So this whole feature is less than a micrometer in size, and the Ys are even much thinner. So they use this method also to win an award, which has been set up by the kind of the forefather and the visionary of nanotechnology, Feynman, who suggested that kind of some scaling down of text on the surface is going to occur by the year 2000, and actually by the year 1998 they managed to really use this method in order to write letters which are just nanometers thick and so on a surface and demonstrate that you can write very small things on the micro scale. Now, what is the problem with fabrication by this method?
It's slow.
Yeah, I mean slow even begins to describe it. Because with T-beam, at least you can scan very fast. With AFM, you can't scan that fast. And this is the reason why this can be great technique, but it's not exactly something that's likely to immediately come into technology. Now, one way to kind of improve it would be to parallelize it, right? Instead of using one tip, use many tips at the same time. Again, the group of Merkin has shown this with 2 tips. You can either write with both tips or on one tip, and you can actually dip them in different types of ink, different types of surfactants. So this is how you have the same features reproduced on 2 different sides. Or this is how you can have the same features with 2 different types of inks. And this one is from a book about nanobots and similar things, kind of popular nanotechnology. This is a vision at IBM of how you can eventually make enormously parallel readout of the surface, kind of essentially hundreds and thousands of AFM tips, and how you can potentially store information almost at the atomic level. So you can use these tips to kind of like make this kind of like features on the surface, and then you can read them off. The problem is how to scale it up, so you can scale it up by using lots of tips. Now, how successful this is going to be, I can't say. It may be.
Are they going to
It's
align
interesting.
so many lasers on the tips?
Well, the idea here is probably to read them out by alternative technique, perhaps.
Okay.
So the whole things right now, you can go to the IBM Zurich website actually and check out what the project is. But the whole idea is to make kind of like the FM tips in a chip. So the whole movement and readout and so on of the FM is made on a single chip, and you have hundreds or thousands of tips. So we can massively parallel write and read on the surface. This is a polymer which is heat embossed. So if you heat up the tip, you can kind of melt it down and make pits or stretch it out. This is how you store the information, and then you read it by scanning. This is the idea. I mean, it's an interesting idea. Now again, you never know whether this idea is going to beat up the semiconductor technologies, which are damn good. But it's certainly an exciting idea, perhaps. Of course, every time such ideas came up, this is also like related to the ideas of how you make micro devices by fabrication. Let's say you take one part, you take another part, and kind of in a way similar to a factory. You take parts and assemble them together. So how do you assemble a microscopic device? I mean, you can think of tips like that, picking up parts and assembling them and so on. Something that I don't believe is reasonable or feasible. And to know why when we study this class, because I mean, you better do things by self-assembly on a nanoscale rather than trying to fix them together. You can do that, but I mean, you have colloidal forces and you have all types of interactions, and it's difficult to control these interactions. But in terms of reading and writing of information, it's a shown concept that it can work. It may actually work. I mean, who knows? May not. So this is how you would do parallel and using FM. Now again, the thing here is that it's called nanolithography, and it really is. If for your research you just need a small patch of something, you can use AFM to make it. I would say that, I mean, you don't go make a startup company for producing this on a mass scale, but for research it can be great. It's a good idea. Okay, any questions here? We have just a few other interesting techniques. Okay. Now, this is something that's, I mean, I like it, and it's very simple, easy, and inexpensive. Some of our distance students actually certainly can be interested in that, because this is a way of generation pattern and features by inkjet printing. Inkjet these days gets to be pretty good, right? You know that you can buy an inkjet printer like for $200 or less, which has 2,400 dots per inch. But this already goes to microfabrication. If you use these drops to make something or make a pattern, you can pretty good print some feature on your printer. And this is an example. This is actually, I guess you load the printer with some types of metallic particles and glue, and you you kind of spin them around, and this is some electronic element which is made by printing. Now you can see, however, that the feature size here is nowhere the previous feature size, right? That's 600 microns, and that's so 1 millimeter is about this large. So that's not nanofabrication for sure, but then it's also kind of, I mean, like when it comes to money, this is nano and the other one is not. So this, I mean, you don't have to pay that much. I have illustrated here some of the features. Now, one good thing can be used for patterning of proteins and DNA. That's kind of useful because you can load your inkjet printer with proteins, and you can print patterns. And this is very useful for bioarrays, which we're going to study not the next time, but the one after next. In principle, you can print your bioarray by inkjet printer.
You put proteins in your inkjet printer.
Well, maybe not the inkjet printer that you have in your lab, but in principle, yes. That's how bioarrays are made. And some laboratories even have these such devices. It's an inkjet printer for protein arrays. Kind of essentially, and you can put also DNA, of course. So that's how people make those. If you have seen all those colored images of different types of hybridization and so on, they are either made by stamping or some kind of lithography, or they are made by printing. So it can be used for such. So inkjet printer happens to be like a very, very useful feature. I remember the time when inkjet printers were considered really kind of some kind of crappy alternative to LaserJet. But these days, in terms of resolution and in terms of features and so on, they're very good. So you never know how technology is going to develop. And these days, people would say with three-dimensional printers. Very similar to inkjet. So essentially what you can do is you can start you can put polymer in your inkjet printer, and you can start printing, and you move the head further and further out. So then you can design some three-dimensional image, and you can send it to the computer and the three-dimensional printer, and it's going to print your small three-dimensional object by kind of, it really prints out a three-dimensional object.
Does it do it just layer by layer?
Sure. You can actually see it on the object. It's not that precise, but you can design something like that. Well, obviously not from different materials, but you can design something like that with cavities inside, whatever, and you send it to the printer and it prints out your object. Now, how this relates us to us being colloidal scientists, you can actually load the printers with colloidal suspensions, and you can do three-dimensional colloidal aggregates. Now, they're by no means precise, ordered, and so on, but in some cases, you just need, let's say, an aggregate of particles of some specific shape. You can print it.
Who manufactures this? Do you know?
This technology is called Maple V or something like that. You can buy it from companies, and this by no means cheap.
So rapid prototyping, that's what it is.
Yeah.
Right?
I don't know why. There may be even more one around
There's
here.
one in workshops.
Yeah.
Many machines from there.
Right. Of course, the quality, the complexity depends and so on. It's not cheap, but it's available. And finally, Now we have studied everything but last time Cellini, for example, told us that you can move things by light. So if you move things by light, you can possibly also microfabricate things by light. Now, you don't have much of a chance if you just take a photopolymer and start illuminating it through a microscope, for example. The reason is that the focal distance and so on, I mean, it's going to spread out. However, you can take some special photopolymers which are called, this is called two-photon initiation. This means that in order to initiate polymerization, you have to hit the polymer with 2 photons at the same time. This makes it very strongly dependent on the intensity of the light. If you don't have the right intensity, you don't have polymerization because the chances of 2 photons hitting the molecule at the same time are negligible. So this allows you actually to focus the laser beam or whatever and make 3-dimensional structures by photopolymerization. This is an example of one structure like that. You can see the features, but it's 3-dimensional features. So it's 3-dimensional stack of like wood pile stack. You can make different waveguides and so on, photonic materials. The problems are that you can see that the features are not that large. And you can see that also, you can imagine that this takes time to scan.
Would that be in a rather dilute solution? Like you're talking
A
about
photopolymer or?
Yeah.
No, it's actually dense photopolymer. The problem is to make this photopolymer to be very sensitive to high light intensity. So it's a kind of threshold type of photopolymer. A regular photopolymer is going to polymerize strongly in the strong light and not that strong in the not strong light. But this means that your features are going to kind of smear. This photopolymer gets photopolymerized only when 2 photons hit it at the same time. And 2 photons hit it at the same time only in the area of high intensity. So this is actually a paper which was published in Nature very recently. And I mean, these guys have, they're not the first to discover this method. They claim that their novelty is developing this special photopolymer. Because you can't do this easily with regular photopolymer. Yeah, yes, Daniel.
You said something about a waveguide. What is a waveguide?
A waveguide in this case would be, this is the waveguide. Now this is essentially a feature. If you shine light from the back, it's going to start refracting and now you can make a microscopic lenses on that scale. This is 1/10 of a millimeter. If you make features like that, this is a photonic material, photonic crystal, and we're going to speak about that in the lecture before the last lecture. This is my area of research in many aspects. So if you shine light here, this is going to act as a kind of, it diffracts and reflects and so on within this material, and it reflects on a wave scale. So kind of you can think of this is comparable to the wavelength of light. So it resonates and kind of resonates until the light gets concentrated here, and then it gets transmitted by the thin waveguide.
So is that like a fiber optic?
Yeah,
cable
yeah,
as a
sure,
waveguide?
yeah. So this is a fiber optic on chip, but this is so small that in order to put any light in it, you have to have this collector, right? And this collector is very complex. It's not just like a funnel opening. It's a special features which allow the light, kind of diffracts the light to go into the waveguide. It's cute, but again, like there are many limitations here, so you don't know whether this is going to work that great. But it's a method which you have to be aware of. And finally, just the summary with a characteristic feature size that you can obtain by different methods. You can read this at home also, but you can see that actually the best and the most expensive is C-beam. But you have a variety of options. Depending on what you want to do, you can make microfabrication on many scales by many methods. And some of these methods are as simple as a beaker in the lab. So, I mean, it's also a matter of imagination. Okay, let's finish here. Time is up.